Hi all, Mr. Yeager, doing a lesson for AP Physics on harmonics. So we're first, it's kind of continuation of the sound unit. We just finished Doppler. So now we're getting into another section where we do use a bit more math to try to figure out harmonic frequencies and what we can do to change the frequency and change the wavelength and change the velocity basically on different types of problems. So before we get to all that, we have to talk about what are called standing waves, because this is what we're going to see in a harmonic frequency. Harmonic waves are going to be standing waves, different versions of standing waves. And a standing wave, the official definition for it, is basically an interference between the incident and reflected wave. Basically, when you send it down to a particular point and then it bounces back. This is a better kind of picture of it at the bottom there, if you look near the bottom. The two diagrams at the bottom are showing you standing waves. Basically, the standing wave, we call it that because if you actually saw one, it looks like it's staying in place. Like you don't see the flow of the wave traveling through the entire string, the entire slinky. It almost looks like it's just vibrating up and down in one particular section, like you see in the second diagram as it goes up and down, up and down. So that's why we do also call them standing waves. But understand, this is a standing wave. Let me get my pen out. The standing wave you see on the right is basically illustrating one wave going toward a fixed end and then basically what happens to it when it comes back. Well, we know when it hits a fixed end, it gets inverted when it gets reflected back. This diagram over on the left-hand side is showing you the incident wave going in and then the reflected wave actually coming right back. So it's kind of showing you if you just, but like that one's trying to show you if we just keep on shooting waves down, we'll basically have this particular pattern develop where it looks like that wave is oscillating between the crest and the trough in one position. All right, that's what we're looking at there. So the shape of the wave and all that stuff we're going to have to be able to look at as well. We're going to have to be able to count waves very well here to help us figure out which harmonic we're about to talk about. Two terms that you'll see come up with harmonics, nodes and antinodes. The definition is pretty clear there. The nodes are the spots where they never change position. When this one was oscillating, that was basically, like, energy is still going through the node, but that's basically where we have perfect destructive interference occurring all the time. And so it looks like they don't basically move at all. While with the antinodes, that's basically where we have some constructive interference occurring, and it's basically the crest or the trough. Okay. Now you got to be careful on this one. Like you see, I basically did for one wave. There's 4 antinodes on that one. I could just count all the crests, but you never count crests and troughs if you have a double wave like you have down at the bottom here. So the nodes is where there's no motion. It's stationary. Antinodes where you have basically the highest velocity, the highest amplitude. That's where it's moving very, very quickly. That's where they kind of pull that in, antinodes. You'll see them talk about the velocity of the antinode. That's because it's going to be moving from here down to the very bottom in very short periods of time. So that leads us to harmonics. Okay. So harmonics, kind of, I start off with a little bit of a vague definition. They're waves that are whole number multiples of a fundamental. And right there, you're immediately going, what the heck is a fundamental? That's on the next slide. Okay. And these are waves that if you hit that particular frequency, they're going to actually resonate. All right, which means they're going to get stronger and stronger and stronger. You can create one sound, and then it just gets louder and louder. We do a lab with tuning forks where you place them over what's called a resonating tube, and basically what you'll hear is that sound will amplify. You'll hear a higher volume because it's constructively interfering, and therefore creating a louder and louder sound, since volume depends on amplitude. Two things to understand with harmonics, because we're going to look at 3 different harmonic situations. Nodes are always at fixed boundaries. Okay, we're going to talk about situations where you either have 2 fixed boundaries, or one fixed boundary, or no fixed boundaries. If there's a fixed boundary, we have to have a node at the end there in order to create a resonating harmonic frequency. When there's an opening, no fixed end, there has to be an antinode there in order to fit the appropriate harmonic. And again, this will make more sense as we continue to see some pictures and stuff. All right. The thing is that we went, like that definition was, harmonics are whole number multiples of a fundamental frequency. The fundamental, which is also known as the first harmonic, okay, is the lowest frequency of sound that will end up resonating. All right, and this is important for musical instruments and again, just testing sound labs in terms of we want to find what is the lowest pitch that we can use with maybe that particular instrument, and it all depends on the instrument. All right, this is basically why. If we go through the 4 classes of string instruments from violin all the way down to a bass violin, bass, cello, whatever you call it, bass, let's just call it that, that's what it's also called. All right, they have different fundamentals. All right, so a fundamental is not a constant. It depends on the instrument, it depends on the situation at hand. But it's the lowest frequency of sound that's going to create this resonating frequency that can amplify. All right. So like I said, all other harmonics, I'm going to put like a little star here, because there's an exception to this, all right, are going to be whole number multiples of this fundamental frequency. So if I start off with a simple problem, let's say there's a fundamental frequency of 50 hertz, and every harmonic of it is a whole number multiple. So if this is harmonic number 1, fundamental, the second harmonic would be 2 times 50. All right, the second harmonic would be 2 times this 50, which what does that equal? Very simply, it equals 100. So the second harmonic frequency of the 50 hertz fundamental is 100 hertz. The third harmonic would be, and this is where people make a mistake, it's not that I double the next number. Everything is a whole number multiple of the fundamental. So the second harmonic is 2 times the fundamental. The third harmonic would be 3 times the fundamental. So the third harmonic, if it's this particular situation, would be 150. The fourth harmonic, 200. The fifth harmonic, 250. The questions on the AP test you with harmonics and this fundamental frequency stuff, usually in questions where they say, you create this particular frequency, which of the following is a possible harmonic frequency? And that's where people could possibly make a mistake, okay? Because it's not going to just be always a simple double, 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 okay? Now this one's kind of pretty straightforward, but there's going to be an exception that they love to throw at you, okay? So always whole number multiples. They could go backwards. If I said the fifth harmonic is 500 hertz, what is the fundamental? The answer would be 100 hertz, because the fifth harmonic must be 5 times the fundamental, so the fundamental must be 100. All right? So this page really is just kind of illustrating that instruments use these. A guitar string has a number of frequencies that they can naturally vibrate at. All right? And this is, again, the importance of the development of that particular guitar, the mastery, the artistry of developing that particular instrument. Is it has to be made very, very particular to create these natural harmonic frequencies for a particular guitar string. Okay? But the thing is, with that guitar string, we can then manipulate it based on kind of where you place your fingers. And that's basically what we have going on here some, is where you place your finger, or how it basically is able to create these different harmonics, depending, again, where you place your finger on it. Okay? So I'm not worried about the math just yet. We'll come back to that. I think it's on the next page, actually. This prior page is something you can always click on. It basically allows you to play around with harmonic frequencies and visualize them. So, what I mentioned, there are 3 types of harmonic situations. The one that I kind of initially showed you, and with the guitar example too, is where we have a string fixed at both ends. All right? And what follows is basically the picture of the fundamental frequency. All right? So, if I have strings fixed at both ends, that means I must have a node at both ends. Okay? And there's only certain frequencies depending on this length, this straight length, not an arc length. There's only certain frequencies depending on the length that will make sure that there's a node and a node at either end. And if that's the case, it'll create one of the harmonic frequencies. The picture you see here, and I think there's another page of it, where basically it's just one side to the other, is the fundamental harmonic for every fixed end, the fundamental harmonic shape for the fixed at both ends harmonic, for the fundamental frequency, okay, is always going to look like that. The second harmonic we'll see on another page, but that's what the first harmonic looks like. You can see it has two nodes and one antinode in the middle. Okay. The other situation that they love to do is what's called a closed-end pipe, where basically one side is closed. We have one end that's closed or fixed and the other side that is open. It doesn't have to be a pipe. This could be a string that you have fixed at one end and then you allow it to whip around at the other end. Okay? Same thing. Depending on the length of this tube, of the pipe, of the string, L, length, okay, it will fit certain harmonic frequencies. But you can see on this one, because I'm closed at one end, it has to have a node at one end, and at the other side it has to end with an antinode. If it doesn't do that, if the wave can't fit that way, it's not going to be a harmonic frequency. Okay? And again, what I mean by that is maybe there's a wave that's like going up and down, up and down, up and down, and ends right in the middle. That particular wave that I drew would not create a harmonic frequency. Okay? So it has to begin with a node and end with an antinode, or whichever way you look at that. It has to have a node and an antinode at the ends. The third situation, all right, is an open-ended tube, where now both sides are completely open. This would be flutes and bass, brass instruments, where you have openings on both ends, essentially. Okay? Since it's open on both ends, I have antinode, antinode. So this is always kind of a weird wave for people to see, where basically you start at an antinode, go through, we do have a node in the middle, and then it's an antinode on the other side. And essentially what happens is you keep on sending these waves through and it'll create some resonating frequency. So again, I'm trying to show you all what the first harmonic frequencies and wavelengths look like for the three situations. And you're going to be able to calculate those. So, the one that people find generally the easiest is the fixed end example. And what you see here is I have basically the first 6 harmonic frequencies for fixed ends. What happens is, the way these are drawn is I go, okay, what's the easiest way to connect these two dots, since it has to be node, node? Well, the easiest way would be just creating that type of a shape. What would be the next? What can I do? Well, I can make one where it goes up and down, but it has to end back at a node again. And so that's basically what we're doing. As we keep on going, I still have these two fixed ends. I just see how many waves I can fit in between them, but I have to end on the node. And then basically I can keep on fitting more and more waves inside of it. Okay? So, what do I then do with this? What you're primarily interested in is, you're interested in basically relating this back to velocity equals frequency times wavelength, our wave equation. Okay, we're going to be interested in going, what would the frequency be? What would the fundamental frequency? What would be the second harmonic frequency be? What would the wavelength be? That would be the things we'd be most interested in. Okay. So, how do I figure that out if it just says the length of the string is L? Well, what I have to do, and this is where it becomes a little bit more visual, is you need to go, well, how many wavelengths do I see right here? And again, I only need to look at one side because it's the side coming back. Well, how much of a wavelength is that right here? This right here, going all the way across, is only a half a wavelength. So this length is fitting 1/2 wavelength. So the wavelength of this wave must be equal to 2 times L. That's basically where we're playing around with these harmonic frequencies. And again, that's good for the fundamental. The fundamental, we sometimes call it the fundamental wavelength, is equal to 2L. And that works for every single fixed end problem, because that's what the first fundamental frequency will always look like. When I get to the second harmonic, well, now at the second harmonic, I have fit an entire wave in that length L. So this length, in this case, equals the wavelength. The wavelength and the distance are exactly the same. So now I have a full wavelength in there. All right. Now this relates again back to harmonics, because wait a minute, I double my wavelength. Okay. I double the wavelength is basically what we're. Oh no, sorry, I don't double my wavelength. Okay. I actually half my wavelength. My initial wavelength is 2L. My second wavelength is just equal to L. So my wavelength is getting smaller, which makes sense because I'm fitting more waves in between the two notes. So as my wavelength gets smaller, if I decrease the wavelength and my velocity stays the same, which it will in this case, I must increase my frequency by the exact same amount. So if I decrease by 2, the second harmonic must be 2 times the fundamental. So that's where we get where fundamental 1 is always a whole number multiple of all the other ones. And you can just keep on going down the entire list. And that's what we'll practice quite a bit in class too. All right. So basically that's what I just talked about. The first fundamental will equal 2L. That's actually something semi-worth like going, okay, I'm going to remember that. For fixed n, the fundamental frequency is equal to, or fundamental wavelength is equal to 2L, the 2 times the length of the string. Okay? What that then leads us to is we can plug that into the formula. Okay? If I'm trying to find the fundamental frequency, F1, all right, it'll equal, again, if I just rearrange my formula, put V to the, oh, sorry. Silly. Bring wavelength to the other side. Fundamental frequency equals V over lambda. What am I going to replace lambda with? 2L. So this is the fundamental frequency of a fixed end situation always. That's the nice thing. Always. So it's V over 2L always. Okay? And that's what I have right now. String instruments, pianos, etc. All right. Kind of going on sidetrack a little bit. How can we then change the pitch using the string instruments? Well, pitch depends on frequency. Okay? If you tighten the string, what will that change? That changes the velocity. We've talked about that in terms of tension, all right, early on. With tension, if there's a greater tension, there's going to be a faster velocity. Those particles are tighter together, all right? So there's going to be a greater velocity that develops, all right? What will stay the same? Well, if I'm tightening the string between two ends, even though I tighten it, the length will stay the same. The wavelength will stay the same between these two. All I'm saying is I'm not going to draw a guitar because I can't. If I have this string and I start tightening it and tightening it and tightening it some, the distance between those 2 points stays the same on that guitar. It's not like you twist it and the string gets shorter. It doesn't snap and come toward it. So velocity will increase, wavelength stays the same, so what will frequency do? Well, my formula is velocity equals frequency times wavelength. If I increase the velocity, keep wavelength the same, frequency must increase. I'll increase the pitch. Okay? That's why when you're tuning an instrument, as you tighten it, the pitch goes higher, higher, higher. If you loosen it, it goes lower, lower, lower. All right? Another thing kind of going along with this guitar stuff, all right, is why does that person constantly change their hand position? Okay? What does that do? Because we know, I mean, you think about it, if that guitar person, man, I'm musical, okay? If that guitarist basically brings their hand farther down along the neck of the guitar, you hear a higher pitch. You get those little wrist wires like at the very bottom, okay? Versus a very big bass guitar where the guy's basically holding the top and strumming, and it's a very low sound. So what makes the difference there? Why is it so high a sound when you have your hand so far down the neck of the guitar? Okay? We can change the length or the wavelength of the string, because what you're doing is when you place your finger against the guitar, so I mean, again, these are going to be terrible pictures, but let's say I have it set up, but you place your finger right here. You're basically creating another node, and therefore now the length of the string that's actually vibrating is very, 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 very small. But did you change so the wavelength is changing, but the velocity stays the same because you didn't change how tight the string is. So the velocity stays the same, so the frequency will change with wavelength. How does that work? Velocity equals frequency times wavelength. If I keep velocity the same and I decrease the wavelength, okay, or if I look at this formula, V over 2L, if I decrease to L, I'm going to increase the frequency. So that's why you hear a higher pitch when the person brings their hand down along the neck of the guitar. What about closed-ended pipes, like wind instruments? Well, we get a little bit of a different shape, and initially people kind of struggle with this because they don't really, again, see it very well. How much of a wavelength do I have right here? All I have right now is that. Well, I know, we just went over this, this is a half a wavelength. So this right here is only a quarter wavelength. So if I have an instrument and I know the length of that instrument and I'm playing the fundamental, I'm only playing a quarter of that wavelength. So L equals 1/4 wavelength, which means the wavelength, the fundamental wavelength, equals 4L. That's important. So this is the other main situation. There's a third one, but you'll see it follows one of the other two. So a closed-ended pipe doesn't follow the 2L model. It follows the 4L model. In addition, the other frustrating thing about closing pipes, or initially difficult thing, is the second harmonic, the second wave that I can create, looks like this one. This is the second harmonic. All right? But the thing is, how many waves do I have there? Right here, L would equal 3/4 wavelength. It's not a full wavelength, it's 3/4. So this would become 4L over 3 wavelength. Well, what did I change there? I decreased the wavelength by 1/3, which means the second harmonic is 3 times larger. And it turns out if I keep going, I can only get odd number multiples of the fundamental for a closed-end pipe. There is no even number multiples. So there's the two main properties of closed-end pipes. All right, is that in the end your formula will be V over 4L, so not over 2L. All right, and you can only get odd number multiples. And again, people struggle with this. So going back to the 50 hertz fundamental, if I'm doing it on a closed-ended pipe, the second harmonic is actually 150. Because there is no 2 times 50. There's no second frequency. I actually have to go to 3 times. And again, people struggle with that because they go, isn't that the third harmonic because you're multiplying by 3? That's where this doesn't completely work. Okay? We have to understand where we're going. This is the second harmonic. This is the second sound that you can make from this particular instrument. So that's where you got to be very, very careful understanding which situation you're looking at. Oops, sorry. Almost done. As for the open-ended pipe, open-end tube, all right, it ends up following the same rules as the fixed end. So you'll be able to have all the multiples of, all whole number multiples of frequency, and it goes back to using 2L again. That's because you start at an antinode, you go down and end at an antinode. This is a half a wave. That's actually a half a wave. And again, people struggle seeing that, but that is half of the wave because if I go back up, that's one whole wave. So I only have half the wave, so if I know the distance, if I know the length of the tube, this will be L equals 1 half wavelength, wavelength equals 2L. So open tube works exactly the same as fixed end. It's closed end, all right, or one side is fixed. That's the weird one. Okay. And so to summarize everything at the end here, the way you approach these problems is recognize, are you talking about a fixed or closed-ended wave? Again, technically add in open, but remember open goes with fixed. But identify your situation, because if you don't, I don't even know what you're doing with the problem. You're going to just take a random guess and hopefully be right. Okay? But after you realize that, go ahead and obviously try to find that fundamental frequency, see if it's given to you. And then all the harmonics will either be whole number multiples if it's fixed, or odd number multiples if it's only one side is fixed. And again, we have to go with a fixed, we're going to use wavelength equals 2L for the fundamental. For the one fixed end, wavelength equals 4L. Those are going to be very popular things to try to remember. All right, I believe that's it. Yep, Beats is a separate video. Thank you very much.